Okay, so here we have the general solution for Laplace's equation in spherical coordinates. And what we must do now is look at what happens inside and outside our sphere. So first of all, let's look at what happens inside. Okay, so consider the two constants, A and B. Well, what we can see is that B must equal 0 for all of L, otherwise the potential will blow up at the origin. So what we can do is we can write the potential inside as or theta should be equal to the sum from L is equal to 0 to okay, so this is for inside. What about outside? Okay, well, for outside, what we see is that A must equal to 0. Otherwise, the potential would not go to 0 at infinity. Now, however, we do have a contribution to the potential from the electric field presence, or it's the potential due to the exciting field. Okay, so that is in. So the potential now outside depends on R and theta is going to be equal to minus E naught R cos theta plus sum from L is equal to 0 to infinity R plus 1 okay, so those are the expressions for our potentials inside and outside. And what we're going to do now is look at the boundary conditions, and we're going to solve for A and we're going to solve for B. Okay, so let's do that now. Okay, so for the first boundary condition, what we're going to have is the potential is going to be continuous across the surface. So we have the potential in will equal potential outside. And this is for R is equal to the radius. Okay, so now what we're going to write is we're going to have the sum from L is equal to 0 to infinity A infinity. Okay, so now this is what we have to solve. And in order to solve this, what we're going to do is use something that's called Fourier's trick. And this is since the Legendre polynomials are orthogonal functions, what we can do is we can integrate them between 0 and pi. So we'd have PL cos theta prime cos theta sine theta d theta, and whenever L does not equal to L prime, the answer is going to be 0. Okay, so it's going to equal 0 for L not equal to L prime. Now, one thing I should mention is this expression here, of course, could be written out in terms of a Legendre polynomial, and it would be given by E naught or by P1 cos theta. Okay, so now let's look at this. Let's look at this for when L does not equal to 1. Okay, so when L does not equal to 1, well, what this means is this term here, that's going to equal to 0. Okay, and so what we're left with is A, and I'm going to substitute little r for the capital R, which is the radius. Equal to L divided by R L plus 1. Okay, so that's the first one. And now what happens whenever L is equal to 1? Well, whenever L is equal to 1, we're going to have A1 by R equal to minus A0 R plus B1 divided by R squared. Okay, so these are our first two expressions which we have obtained by solving for the first boundary condition. Okay, now let's move on to the second boundary condition. Okay, so for the secondary boundary condition we have the discontinuity, so we had epsilon and the derivative of the potential inside with respect to R will equal to epsilon naught by the derivative of the potential outside with respect to R. Okay, now recall that our relative permittivity was equal to epsilon divided by epsilon naught. Okay, so now I'm going to write this out in full, and what we have on the left hand side, epsilon R, we have the sum Okay, so there we have it. So now what we must do is something similar to before. We'll use Fourier's trick in order to determine what the constants A and B are. And we're going to do this for when L is not equal to 1 and for when L does equal to 1. So first of all, when L does equal to 1, this is going to go to, when L does not equal to 1, this is going to go to 0. So what we're going to have is epsilon R by A L plus 1 to L plus 1 L divided by L plus 2. Okay. And then whenever L does equal to 1, what we will have is ER A1 R squared will equal to minus E naught plus 2B1 divided by R cubed. Okay, so now what we can do is, using these expressions, we're going to relate them to the expressions that we found for the first boundary condition. Okay, so let's do that.